Oh, check the audio devices. Okay, I just have to do a little test here and then we can get started. Hello. Okay. Computer is always like iffy on whether the audio is going to work. All right. So yeah.
By the way, how many days of lectures do we have left? I guess weeks.
Isn't it like 2, 3? Yeah. So, yeah. I know the time goes by so quickly. I mean, every time, every class.
I feel like term 2 is like short. Is it like actually shorter than term 1?
I think it's just that you've already been through the first one.
Yeah.
And then you're like, oh, okay, you know, kind of like maybe it's an exposure thing, but anyway, so hi everybody online and hi everybody here.
I think maybe in that way I should probably stop procrastinating on seeing if I need a diagnosis.
Definitely don't procrastinate. Yeah. So, this guy didn't show up. Definitely, you know.
That is one area where I'm fine because I will hyper fixate on like appointments I have to the point where I cannot get anything else done that day. Where I will have an alarm for like when I have to go, an alarm for when I have to like start getting ready, and sometimes I'll have to set an alarm later the next day.
Yeah.
Or an alarm to get up in the morning that like reminds me of the thing I have that day. That's the one thing I don't have issues with.
Yeah, I would say, and you know, I'm not that kind of expert, but you know, Carleton does have some pretty good resources in place.
Yeah.
Definitely take advantage of them. You know, it'll be beneficial, you know. So let's pick up where we were, which I think was this slide. We were talking about, you know, the neocortex, which is kind of the thing that really differentiates human brains from other mammal brains. The neocortex is significantly larger in humans, right? It's that folded, you know, the exterior of the brain that you're all familiar with if you've seen a picture of the human brain. So I think we talked a little bit about the difference between gray matter and white matter. So the cortex is made of gray matter on the outside, and it's gray because it has unmyelinated fibers. The axons and the dendrites don't have a myelin sheath. A myelin sheath is like a protective coating, you know, a bit like the insulation on a wire, if you want to think of it that way. And underneath the white matter, it has myelinated axons, and well, people are still arriving here. So it has myelinated axons, and myelin looks white under a microscope. So that's why we call it white matter. And we have two main types of neurons in this area of the brain. Those are the excitatory pyramidal cells and inhibitory interneurons, which, if you recall, the excitatory one sends signals and the other sort of dampens things down a bit. And most of the cortex is actually arranged in these layers here. So we've got a layer on the outside. We've got cortical columns beneath that. And it's interesting to note here that the sensory areas of the cortex are actually kind of organized in this hierarchical manner. The reason that is because these systems are, in fact, modular. If you want to think about a system like vision or audition, there are certain steps in those processing streams that are each handled by a different sort of system in the brain, right? Like the visual cortex. Once information comes through the optic nerve to the visual cortex, it goes to area V1 and then to area V2. And then you'll never guess V3, 4, and 5. Yeah. And each step up the hierarchy is more complicated until you go higher and higher and you get, you know, a visual experience. So, and also what's really important are these cortical connections and cortical thalamic connections. They link different areas of the cortex together.
Am I hearing cortical correctly? Is that what you're saying?
Yeah, I mean, you could say cortical, like with an L.
No, but like it is like the same root word.
Yeah.
Like, connected.
Yeah.
So it's like a loop in a sense. Right?
From one area of the cortex to another.
Oh, yeah.
Yeah, exactly. And then the thalamocortical loops, the thalamus is sort of deeper in the brain, right?
I
Under
wanted
the,
to make sure I wasn't having a stroke.
yeah, no worries. You're good. Oh, and we have the, well, we're already familiar with this. Oh, what slide number? It's always asking which slide number. Let me find out. Yeah, right now we're on 14. Yeah. So 14, slide 14. You know what? Maybe I can quickly just add some slide numbers here. And then I'll always remember what slide I'm on. And then I can tell the people who are not here.
Same problem right now. I'm waiting to look and I keep forgetting to get a bookmark for it.
So all the pages get dog-eared? Or-
No, I just have to I have a vague recollection of where I was, and then every time I sit down to read it, I have to flip back and forth through it to narrow down where I was.
Oh, that's exactly, I can't see the slide numbers. Oh, that's exactly what happens with these every time I come back, but okay, so we're on slide 14. I'll just have to try and remember that. So yeah, we've encountered this before, the brain's contralateral division, right, into two hemispheres, and by and large processing from the right side of space takes place in the left hemisphere and vice versa, right? So we have these two hemispheres. They're connected by the corpus callosum, which is the larger sort of network that connects everything. And there's also the anterior commissure, which is a smaller sort of bridge. Sounds fancy. Yeah. So we've got 4 lobes for each hemisphere, and they each have their own sort of specialized functions, right? The occipital lobes are kind of in the back, and they deal primarily with vision. That's where the visual cortex is. The parietal lobes have a lot to do with sensory association, so sights, smells, sounds, and it's also where the somatosensory cortex is located. So that's where you would see the, for example, I know this is going to sound weird, but that's where that touch homunculus is. If you've ever seen a representation of a human drawn out over the somatosensory cortex, it shows you kind of like what area the face is represented in. So it's kind of like, you'll see this sometimes. It's a homunculus. It's not like the homunculus fallacy.
Well, one that I'm familiar with is it's like a depiction of the human, but the various sensory parts of the body are scaled.
Yeah.
How much.
Same idea. So that homunculus has really big hands because our hands are really sensitive. And I think a big face with really big lips.
Yeah.
Because
eyes and lips are very.
Yeah, that's the one. Yeah, exactly. So you imagine that in 2D, just drawn over the somatosensory cortex. Yeah, exactly. Yeah, it's perfect. Oh, and the tongue, yeah, silken, that's right. The tongue is in there because it's also, I mean, think about it, it's got to be pretty sensitive to help us taste everything. And I think the nose looked pretty big too, because
there's a sensory and a motor model.
Oh, interesting. Yeah. So those will probably look a little different.
They're similar.
Yeah, but still.
Hands are a lot bigger, and then also the face is a lot bigger.
Huh.
But hands is the biggest difference.
Probably because of the fine motor control. Yeah. Well, you also have the temporal lobes. Temporal lobes are important for memory, but also for audition. So hearing, and the frontal lobes. Frontal lobes are implicated in executive function. So making plans, making decisions, right? Deciding what to do. What am I going to have for lunch? If you believe in free will, the frontal lobes arguably play a big role in that. So that's a basic idea of the brain. Here it is just sort of illustrated for you. And you can see all these are called fissures. The sort of divisions between the lobes there.
Funny that visual cortex that's back of our brain.
It's weird, right?
But that makes sense, right? Because obviously you don't want vision by something hits you in the face.
I suppose not, but if something hits you in the face and yeah, so it's just, it's like I said last time, evolution is a tinkerer, right? So it's always working with what it's already got. Evolution almost never produces an adaptation that's like absolutely completely novel out of nowhere, right? It has to work with what's already there. And probably the reason why it's in the back has something to do with the nervous system of primitive creatures that didn't have very well developed eyes or nervous systems. We're talking about like not even an eye with a lens, but like a little patch of photoreceptor cells. And so those initial conditions kind of result in mammalian brains where vision is processed in the back rather than in the front. So yeah, it's weird what you end up with.
I mean, and it's also corroborated by the fact that like the brains of other like creatures can differ widely in structure. And the conditions that created them are different.
Yeah, well, but there is still, like, everything is still built on top of the previous version.
Like the individual, like even like usually just like the layout is like there's some variety there.
A little bit, yeah. Like, well, even if you look at two human brains just beside one another, they look very similar. But if you were to look at how they were, for lack of a better term, wired with some kind of neural imaging technique, all our brains would look very different, I imagine.
Mine is wired up with so
Yeah. But how is the your brain different than my brain? But they still do something similar, right? They still generate this conscious experience that we have. So what's going on in the brain? One way to understand what the brain is doing and how it might be generating our conscious experience is to look at what is actually happening in the brain that corresponds or correlates with conscious events, right? But it's not immediately obvious what exactly we should be looking for, right? What level of functional organization do we look at? Do we look at the entire brain? Do we look at specific neural networks in the brain, or are there special kinds of neurons that we should be looking for? Like, well, where do we start, right? We could look at cortical columns, and we could model those with neural networks. The level of single neurons, we could investigate that with, single unit recording techniques. That's usually what we do in animal studies. The entire cortex, plural cortices, right? Should I look at my frontal lobes, my parietal lobes? Or as before, is it a whole brain kind of thing, right? Also, a warning about causation and causality, right? We can look for stuff in the brain that correlates with certain elements of our conscious experience, but we have to remember that correlation does not automatically imply causation, right? I think about it. You could have two events, A and B. A is correlated with B. So here's some possibilities. Maybe A caused B, but it's also possible that B caused A. Or A and B were caused by something else. We'll call that C. Or maybe A and B are the same thing, and they just appear to be different. I think the example that Blackmore gives in the textbook here is that of a train arriving at a stop and all of the people going to the train, right? What's happening? If you knew nothing about what was going on, you might say, oh, the train caused all those people to show up. Or you might say the people showing up caused the train to come. But what really happened is something else, C. the train's timetable, which the train is following, brings the train to the station and all the people at the same time, right? And if you knew nothing about trains or people or anything, you might get things mixed up, right? So we have to do that too with the brain, because the brain
It's exponentially more difficult to do that accurately, the more complicated the system works.
Exactly. And like we were talking last time, the brain is usually talked about as if it's the most complicated thing in the universe. And maybe that's true.
Not true, it's JavaScript.
So, okay, neural correlates of consciousness, what you think of them, maybe depends on where you sit theoretically. So let's talk about some of the metaphysics here. Or wait, no metaphysics. No, we're going to talk about unconsciousness. Just a reminder of the metaphysics, though. You know, we're talking dualism, physicalism, right? Idealism, things that you may have, discussed in a previous critical response or that we read about much earlier in the class. But unconsciousness, maybe we can learn about neural correlates of consciousness by looking at brains that are not conscious, right? Because think about it, if we could understand the difference between a conscious and unconscious brain, if things are simple, which they're not, but if they were, well, then we would know, right? Just subtract the activity of an unconscious brain from the activity of a conscious brain, and that difference is the magic difference, right? Maybe. Well, there's a few different kinds of unconsciousness, right? One is not even a type of unconsciousness. It just sounds absolutely terrifying. It's called locked-in syndrome. Here you're locked in, your muscles are paralyzed, but you're still conscious actually, right? So, yeah. No, that sounds terrifying. Sounds like something from a horror movie. Similar, there's anesthesia awareness is something that occurs quite rarely. But basically it occurs when someone goes under anesthetics for surgery and they're paralyzed, but they are still conscious and they can feel, yeah, it's pretty terrible, right?
Usually does very nasty things to their psyche.
Oh yeah, that would be just, ugh, that's nightmarish. Yeah, so locked-in syndrome, anesthesia awareness, very scary. Zoe asks, is this the same as having memories from a coma? Not quite, no. A coma is a different kind of state. And we'll talk about that in just a moment. But yeah, a coma is a bit different, right? For example, a coma is kind of like, on one side of a persistent vegetative state. On the other side, a minimally conscious state might be something like when you're waking up, or maybe when you're really drowsy or something, right? So a coma, there's no awareness. Is it like sleep paralysis? Sort of, maybe. Yeah, well, let's talk about that after. I'll just finish this and then we'll go back to that. Yeah, persistent vegetative state, you have ostensibly a person who seems to be awake, but not aware of anything going on around them, right? Does everybody, maybe, I don't know, maybe you don't, maybe you won't remember this. Depends on, I'm showing my age here, but the case of Terry Schiavo. Yeah,
I think I might know which one.
You may have heard of it. She was in a persistent vegetative state, and there was a legal battle that sort of entered the public conversation about whether to take her off life support or not, because she was alive and she was awake, but not aware of anything. Vegetative state, you're just like literally, that's when we say so-and-so is a vegetable. Like, what does a vegetable do? It It grows, it's alive, but it doesn't do anything. It's not aware of anything. It doesn't move around, right? So that's kind of in between a coma where you're right out and a minimally conscious state, which would be, I guess, as I mentioned earlier, like waking up. So yeah, Silken and Iman asked about sleep paralysis. So what is the deal with sleep paralysis? Well, in normal cases, when you dream, you enter a phase of sleep called REM sleep, right? And when you're in REM sleep, most of the body is paralyzed. Your lungs work, obviously, and your eyes can still work, but you're paralyzed. And this is why you don't get up and act out your dreams, for example, right? That wouldn't be adaptive. Imagine if you were dreaming like, oh, I'm in a beautiful forest, but really I'm about to walk out my bedroom window. I'm like, oh, I want to see what's around the corner. But in real life, I fall to my death.
Is that what sleepwalking is?
No, actually, sleepwalking does not occur in REM sleep. It occurs in non-REM sleep. Yeah. Yeah, it's counterintuitive, right? A lot of people think, oh, if I'm sleepwalking, maybe it's because the bit of my brain that's supposed to be off is on and I'm walking around and acting my dreams out. But actually, no, sleepwalking tends to occur in a different phase of sleep where sometimes in non-REM sleep, dreams are reported, but they're not visual. They tend to be like thought-like. Like if you wake someone up from non-REM sleep, they might be like, oh, I was just thinking of so-and-so, right? But if you wake someone up from a REM dream, it's like, oh, I was just having this dream where all this stuff was happening, right? What's that?
What is the thinking? Sorry, my fault. What is the thinking dream? Like all dream kind of stuff?
Well, I guess like by more thought-like, I mean, there's not really a visual component to it. I mean, most people's reported dream experiences are a lot like, you know, this, except for all the absurd stuff that happens, right? Like, I don't know, my dreams are very stream of consciousness, and I tend to like go with it, right? So I'm gonna try to think of an example. Well, like maybe if this were a dream and someone else entered the room and said, oh, something's happening over here, we have to go do this, I'd be like, oh yeah, bye, and all of a sudden I'm off doing something else, right? Yeah.
I rarely remember dreams that are like progression of events type things that are like coherent anyway. But about like once or twice a year I'll get ones that I do remember, and every single time they are traumatic.
Oh, that's unfortunate.
Like as in the last one I had was last October, and without going into too much detail because the description itself is terrifying, it was straight up psychological horror.
Oh yeah.
I was not in a good spot the entire day following.
Yeah, no, that's rough. But it may not be a bad thing. Dreams might be the brain's way of kind of defragmenting itself, if you like defragmenting memories and things like this. So, but sleep paralysis, just to answer the question, occurs when something goes wrong, not like seriously wrong. It happens from time to time where you will become conscious, you'll wake up, but your body is still in REM sleep mode, and to a certain extent, your brain. So you'll wake up and you're aware, but you find you cannot move. And not only that, but you'll probably also hallucinate because your brain is awake, it's receiving information from the actual physical environment, but it's also still kind of dreaming. And so sleep paralysis is not quite like a persistent vegetative state in that you're aware of what's going on, but weird stuff happens, and people probably reported cases of everything from visits by demons, alien abductions, all kinds of that stuff. It can be explained by sleep paralysis. Back in the Dark Ages, right, there was the incubus and succubus. These were demons who were believed to come and take advantage of you when you were asleep in bed, right? The incubus was a male demon that would prey on women who were asleep, and the succubus would prey on men. But we don't really have that anymore, right? But we do have a lot of reports of alien abductions. And 9 times out of 10, oh, no problem. I'm glad I could explain that. 9 times out of 10, if someone's telling you they were abducted by aliens, they weren't in a field picked up by a flying saucer or anything like that. They were in bed. And they describe it like, oh, you know, I woke up and I couldn't move. And then I saw this light outside my window. And then the next thing I knew, I was in a spaceship. Like, well, sleep paralysis. You woke up, you had sleep paralysis, and then you started dreaming again, which is still a cool explanation. I mean, the brain, like, it's crazy. The brain can do that.
Yeah.
I think dreaming is fascinating. And I think dreaming can tell us a lot about how the brain represents the world, right? Remember the grand illusion, the idea that the world is, you know, this, all this, it's not how it actually is. It's just a representation, like a tunnel through reality, I think was one of the phrases that was used, right?
You know, it's kind of weird, like, sometimes things in the day that, like, you bother you at the time or like impact you, but then you just forget about them and just come up with new things.
Yeah.
But that's good in like your brain anyway.
Yeah. Yeah.
But like you never, when you're awake, you never think of some of those things that you do with it.
Yeah, exactly. Like, and that's why I think Freud was really into studying dreams. He used a lot of the dream imagery that his patients reported as evidence for his psychoanalytic theories, right? His idea, by the way, was that you know, things get repressed in the unconscious. So you have, you know, maybe a traumatic experience or something happens, you know, so your mind stuffs that away in the unconscious. Or maybe you have a fear, stuff it away, just repress it, you know, that's what the mind does. But then it always returns from repression. Freud calls this the return of the repressed. It always comes out. And usually it's censored by the conscious mind, he thought. So that's what he thought dream imagery was all about, right? It's all, you know, fear, sexual desire, but it's symbolized by your dreaming brain. That's what Freud thought. Really, what I think is happening is that your brain is kind of working through everything that happened that day, moving things into long-term memory, getting rid of garbage that it doesn't need, right? Kind of cleaning up, defragmenting, you know, like a malware scan for your brain, maybe, I don't know, or a defragmentation for your brain. So that's why things come up, and that's also why dreams can seem so associative and stream of consciousness like, because memory is also associative. So if I have a dream, you know, maybe I didn't teach on a certain day, but I was reminded of the class I teach. Maybe I was reminded of this class. And then so I have a dream where I'm teaching the class, but then something else happens. Maybe I was also earlier that day at the grocery store. So I might think in my dream, oh, that's right, I have to go grocery shopping. And then I leave the room and all of a sudden I'm at the store. Just once I open that door right there, right? Weird stuff like that. So anyway, functional neuroimaging can be used to look at conscious and unconscious brains. Stephen Lorry's used a kind of electrical stimulation. I think this is a transcranial magnetic stimulation of some kind. But maybe not. It's not actually clear in the book here. But he was able to elicit activity in the brainstem, in the thalamus, and in the primary somatosensory cortex, but not higher up in the pain matrix. Oh, if it's in the pain matrix, it must be an electrode like Liebig on an open brain or not an open brain, but an open skull during brain surgery. So he concluded that persistent vegetative states is actually something caused by a disconnect between primary sensory areas and frontoparietal areas, so areas in the frontal cortex and the parietal cortex. And he concluded, quote, neural activity in primary cortices is necessary but not sufficient for awareness. So at least in cases of the persistent vegetative states, we need activity in the primary cortices, but that's not all we need. We're still missing something here. Or anesthesia. Yeah, we talked about anesthesia a moment ago. Maybe what we can do is give people anesthetics and examine what happens in their brains. Maybe, put you in the functional magnetic resonance imaging machine and give you some propofol or some isoflurane. These cause global suppression of cortical functioning as the dose increases. So the more of these one has in their system, the less activity there is all across the entire cortex, right? But it's not like we've discovered that there's evidence for specific consciousness circuits or anything like that, right? That would be Cartesian materialism anyway, right? That would say, oh, the consciousness circuits, that's where consciousness happens. That's the special place. Yeah, no, when we do this, we don't see that. We just kind of see less and less activity until people are completely unconscious. So for some anesthetics, maybe what's going on is we're suppressing or blocking signaling from the thalamus, to and from the cortex, between the cortex and the thalamus. We don't quite know whether this happens in the thalamus itself or within these loops that we were talking about earlier. But this seems to be similar to what we observe in persistent vegetative states, a sort of interruption between lower and higher areas of processing in the brain, right, between the thalamus and the cortex. But not all anesthetics work this way, notably ketamine, that doesn't really work like this. Sure.
So like, how it's possible to put somebody in the vegetative state, basically, like they did that with the Chinese or Chinese.
Oh, you mean like lobotomizing them?
Yeah, how do they do that?
Well, lobotomies are.
Yeah, but like, what do they do to cut,
Well, I think in most cases like that, the people don't end up completely vegetative, but their behavior is definitely changed.
Yeah, it was usually done to suppress a very specific behavior pattern.
Mm-hmm.
It wouldn't result in like a complete loss of like a ability to function.
Yeah.
I mean, in a lot of cases, it resulted in a significant loss in their ability to function.
Yeah, and of course, if it's done well, I don't know if there's a right way to do a lobotomy, but if it's done the wrong way, then you'd end up as a vegetable, perhaps. But yeah, usually, it's so gross to think about. It's not like brain surgery today where, we know what does what and we can go in and do it surgically.
I'd like to stop thinking about it for one.
Yeah, no, did anyone see that show Nurse Ratched on Netflix? Oh man, the doctor on that show was super into giving lobotomies. It was, what's it? It's like meant to be a prequel to some book. What's the book? Is it Mice and Men? Is it? It's one of those famous books. I don't know. I'm not much of a reader, but anyway,
Really not Mice and Men.
What's that?
I don't think it's a Mice and Men.
No. This is old. It's set in the past, but what am I thinking of? I can't think of it. It doesn't matter. The doctor is like all about lobotomies. He's like, I've got the perfect lobotomy technique and I can make it work. And, he's hammering ice picks up there and, so pretty gross. Well, okay, so maybe looking at cases of unconsciousness are not that helpful. Maybe we can look at conscious vision. So we're going from looking at conscious stuff to or from non-conscious phenomena to conscious phenomena. That's what Francis Crick and Christoph Koch did. They together searched for neural correlates of consciousness. Oh, one flew over the cuckoo's nest. That's it. Yeah, that's what it was. Because cuckoo's nest, the mental institution. Yeah. Ice pick lobotomies. Oof. Anyway, Crick and Koch were looking for neural correlates, correlates specifically to certain kinds of visual experiences, right? And what they thought was going on was that there's a sort of unconscious homunculus in the brain, which quote unquote observes the sensory areas. What's that? Yeah. Well, anytime, even, we don't solve Cartesian materialism by, just putting air quotes around things either, right? Like, oh, what if there's an unconscious homunculus and it just observes, like, okay, but that's the same thing. That's the Cartesian theater, right? I don't know. Maybe it observes the sensory areas, or maybe, they propose that there are actually a lot of networks like this in the brain, right? It's not like we have just one process observing a whole bunch of other processes. We have many processes observing many other processes. So, of this theory, Crick wrote, first you want an idea of whether it's that set of cells firing or whether they fire in a special way, or whether it's a combination of the two or something else quite different. Crick actually ends up settling on this sort of, I think the 40 hertz. He's all about 40 hertz. If activity observed at a certain frequency is conscious activity, but I don't know how that's supposed to explain anything, right? But he's outlining different ways we can think about identifying neural correlates of consciousness. Is it a certain place or group of neurons? Is it a particular pattern of activity, right? If there's a certain type of processing that's conscious and a certain type that is not conscious or doesn't enter consciousness, then what's the difference, right? I mean, I said earlier, this sounds to me just like Cartesian materialism. Anytime you're talking about homunculi or anything like that, you have to watch out, even if you're putting air quotes around everything. So the hard problem remains. Crick kind of ignores it, Blackmore says. All right, here we go, the reverberatory circuits. This is what I was talking about, reverberating at the right frequency, which I believe is 40 hertz. So Crick suggests that there are these circuits that we have between the thalamus and cortical layers 4 and 6, and he thinks these are crucial for our conscious experiences. And McKay has a similar suggestion. He says that, quote, the cooperative to and fro traffic between cortical and deeper levels of neural activity, end quote, are what are important for consciousness. Cotterill, he suggested the anterior cingulate is a site of consciousness. What does that mean? Does that mean it's like a seat in the theater? Is it a screen, a mental screen? Not really. Yeah, like, hey, there's this part of the brain, and that's where I think consciousness is. Yeah, like, well, what does that mean? Like, this is the mereological fallacy again, right? Like, what do you mean that's where the consciousness is? I'm conscious. My brain isn't conscious, but I'm me, the whole me, my brain and my body right here in the environment. I'm conscious.
Because it's so good at saying so little with so many words, they should honestly be called.
Yes, but don't do that. That's why when I say in your essays and in your writing responses, how I say be as simple as possible, don't do that. Right? Don't have like all of the words, but not really say anything substantial or incorrect or something, right? Ramachandran, I mean, I like his work on this, and he's maybe one of these guys that's not super Cartesian materialistic about this, but he writes, the circuitry that embodies the vivid subjective quality of consciousness resides mainly in parts of the temporal lobes, such as the amygdala, septum, hypothalamus, and insular cortex, and a single projection zone, in the frontal lobes, the cingulate gyrus. So a lot of these thinkers, maybe Ramachandran most of all, emphasize that the bits that are observing the other bits are themselves not conscious. It's kind of like, I don't know, I get the sense they want to have their cake and eat it too. Have their Cartesian cake, right? And eat it too, right? They can say like, it's consciousness arises out of, activity in all of these areas in the temporal lobes and projection to the cingulate gyrus, and none of those individual bits are conscious, but that's how consciousness arises. But they still use the language like a projection zone, as if there's a screen. I know it's just an analogy, but this is why Dennett is worried about Cartesian materialism, because even though all of these thinkers are not dualists, they're still using the language that a dualist would use. And Dennett's like, okay, we have to be careful when we do that, because the language we use affects how we think about things. So that's why we have to be careful here. So, that said, this hasn't stopped people from trying to identify where in the brain or when in the brain consciousness happens, what the magic difference is. Let's see, we're still doing pretty good for time. So if you believe the idea of locating consciousness is maybe a bit wrong-headed, we've still managed to identify parts of the brain and implicated them in certain kinds of processing, right? And important for our purposes here is visual experience. Neuroscientists have made a lot of progress in this area, actually, in identifying the neural correlates of visual experience. For example, we know that visual information, light hitting the retina and causing nerves to fire, is transmitted through the optic nerves to the superior colliculus. Once it's there, some information goes to the eye movement system, so that we can direct our gaze and move our eyes around. And some go to the lateral geniculate nucleus in the thalamus. After that, it goes to the visual cortex, and that's back here in the occipital lobe. So it travels through V1, visual area 1, then V2, V3, V4, V5, then to the motor cortex, and on to other areas. Damage to the eyes, of course, can result in blindness, but also damage to the thalamus and area V1. So we know that those areas of the brain are important for visual processing, right? But they don't seem to be sufficient for conscious vision. They're necessary, but not sufficient, right? And we know that because when we're dreaming, like I said earlier, dreams are typically very visual experiences. But when we're dreaming, area V1 is not working. Area V1 is off. Think about it. We don't need it. We're asleep. There's no visual information coming in. So area V1 is like low-level visual processing. We're talking picking out like edges and shades and things like that. Very rudimentary processing. So we don't need that when we're asleep because our eyes aren't open. There's no information coming in. Oh, yeah, I just said all that. Guess I got ahead of myself there. Yeah, so we could also have a patient, like I say in the first point here, where we might observe activity in V1, but if that information does not travel up the processing stream, they won't be conscious. And as I said a moment ago, V1 is suppressed during sleep. When it comes to monkeys, we use single cell recordings on monkey brains. And we can see that cells in the V1 of the monkey cortex can't differentiate between movement that's caused by eye movements and that's caused by the seeing moving. You need cells higher up in the processing hierarchy to do that. So we know that V1 is important for normal seeing, but it's not the whole story. That's what Christoph Koch concluded. He said, while V1 is necessary for normal seeing, as are the eyes, V1 neurons do not contribute to phenomenal experience. They're more to do with getting the information from the environment deeper into the brain or higher up in those chains of processing, that processing hierarchy, such that the brain can generate a conscious experience. Who's seen a Necker cube before? This is a Necker cube. Yeah. Yeah, that's what it's called. It's the Necker cube. And if you stare at it at the right angle, you can get it to sort of flip, right? Like it looks like to me that this is the front. But I can easily, oh, there it goes. Now this is the front. You know, the figure stays the same, but it flips back and forth. Sometimes we call that a Gestalt shift. That's from Gestalt psychology, which says that conscious experience is very holistic. And it's kind of like something we do by engaging with what we're perceiving. Here we have a background and a figure on that background, and none of those things are changing, yet our perception of the Necker cube changes, flips back and forth. And it's an example of an ambiguous figure. There are lots of ambiguous figures. You've probably seen them. Like one is looks like a vase, but also two faces in profile looking at one another, right? Or the duck rabbit. Looks like a duck, looks like a rabbit, right? These are all ambiguous figures. So maybe what's happening is we have two sort of ways of seeing the cube, and they're each competing for consciousness. And that's why the cube seems to flip in its orientation. Maybe that's what's happening. It's interesting. It's interesting because, again, the lines, the background, none of that has changed, but there's two different ways of seeing it that are kind of like, it's like the cube is like, look at me this way. No, look at me this way. And it's back and forth, and the brain can't decide. So it just keeps flipping. I think it's just because of the way really that lower level visual processing works. You know what I mean? But also higher level processing can affect how we perceive as well, like concepts, ideas, memories, biases. And this is getting a little outside of ambiguous figures, but if you ask people to estimate the size of coins, people from lower income backgrounds will overestimate the size of the coin. Like if I'm like, how big is this coin? 2 centimeters, 3 centimeters? People with less money exaggerate their estimates of the size of the coin, right? Yeah, like it's weird though, right? So anyway, binocular rivalry is more similar to the ambiguous figure cases. So in binocular rivalry, what you have is a different image presented to each eye. This could be done with, maybe you come up with a device. You could do it with virtual reality. You could do it with the Oculus Rift if you wanted to. You could just have a special screen and put a divider in the middle. But I show you a different image in each eye. But your brain doesn't combine the images. Rather, your perception flips back and forth between the two of them. Right? Like if I showed you a boat in one eye and an airplane in another, it'd just be boat and airplane, not a boat plane. Yeah.
Sometimes when I kind of space out, I noticed that my eyes tend to drift apart ever so slightly. It causes my field of view to sort of double itself. Huh. And even though I can see almost the exact same things, just if you did twice next to each other, one side is always more dominant than the other. It usually follows my dominant eye.
Yeah.
But it's it just I don't know. It's kind of hard to
Yeah, it's weird. Yeah. But I would say that's similar to this.
Yeah, well, that's
you
what I'm
know,
saying.
yeah. Yeah, go ahead.
So it's a little, not exactly a little thoughtful, but if you're blind, right, and you've always been blind, how do you like, how do you think of that? Like you dream in sounds, or is it just like thoughts?
I'm not sure. You'd have to ask a blind person,
Yeah.
really. But I think it would depend on whether they were congenitally blind, right?
Yeah.
Were they born that way, or was the blindness a result of an injury,
Yeah.
right? And also you have to remember as well that most visually impaired people are not like 100% blind, right? Like maybe they can see shapes but not fine details or something. So yeah, I'm not sure. It probably depends on the individual case, really.
Well,
But
it's
yeah.
interesting to think because like, talking about consciousness and like framing the world through sight, consciousness kind of sight because
Yeah.
I watched a video about like this deaf person, and the question was how does he do, and do people talking with him? And she says they do, which is a very weird thing. Like, they don't talk sign language with them.
Yeah.
She can understand what they say.
Huh. Weird. It reminds me of a very curious account I read about. I think this was actually something that Ramachandran had studied. Similar to this idea that you don't need lower level processing for higher level phenomenal stuff. Maybe that's what explains the case of this deaf person and their dreams. But
if his comprehension of what they're saying is not necessarily like tied to like a sort of like sensory, but it's probably just the language center of his brain doing that work.
it could be. It could be. And some theories of dreams have it that dreams are not experiences at all, but that they're kind of like, almost like, this is Dennett's theory, and I don't quite agree with it, but the idea is that dreams are not experiences that are happening in real time, but they're these automatic, spontaneous memory insertions, almost like popping in a cassette tape. So he calls it his cassette theory of dreaming. So there are certain concepts and memories and stuff that are activated when I'm in REM sleep, but it's only upon waking up that it seems to have been like, there's like a narrative structure to it. And that it was like a linear sort of experience. I don't quite buy it, because there are experiments where we have people who are like lucid dreaming, and they can actually make eye movement signals in a sleep lab in real time to an experimenter who's monitoring them with like yeah, it's nuts. Yeah, I'll talk about that in a moment, but what I wanted to talk about first was Martian colorblindness. Yeah, this is what Ramachandran was studying, and there's this gentleman he met who was colorblind, so he couldn't see certain colors, but he also had a curious neurological condition called synesthesia. So maybe you've heard of synesthesia. So in his case, he had some kind of color synesthesia where, if you're not sure, just for the people online, because I can see everybody nodding here, but not here, right? So synesthesia is where you kind of have this mixing up of phenomenal sort of characteristics. So for example, one very common one is like number, form, color. So number, color, or number, form, color synesthetes will perceive numbers as different colors, right? Like inherently different colors or different shapes. Same with music, lots of different domains, right? There's lots of different kinds of synesthesia. Probably the most common one is, something like days of the week having colors or moods. And it's not just like, oh, blah, Monday sucks. It's like, no, Mondays are always purple, stuff like that, or number lines. Yeah, people can be different colors. The number line is sort of like an automatic mental imagery thing that happens when some people do mental mathematics. It just pops into their head. So that's a kind of synesthesia. So lots of different kinds of synesthesia. Anyway, this fellow had a color synesthesia. So he could synesthetically experience colors that he couldn't see with visual experience. So he can't see the color red, but maybe the number 5 is red, right?
But like he like with his own sort of like observation, he can confirm that he is seeing a color that's like that. There's like
Well, he's not sure what he's seeing.
well, that's what I'm saying.
Yeah.
There is some kind of disconnect there that he can like.
That's why he calls them Martian colors, because it's like he's on another planet or something.
But this red is way different from ours.
Well, I think
Form and experiences as a phenomenon. So you see a number form, or you experience an auditory form, you experience it in a different way.
yeah, but I think that he, like, I'm not sure if how well he's able to distinguish between different colors.
Yeah.
You know, because you have not only is he colorblind, you know, that introduces that kind of worry that the inverted spectrum thought experiment does, right? Like maybe my red is your green, but because they're flipped exactly, we would have no way of knowing that our phenomenal experiences are in fact different, but they're consistent enough that when we refer to, you know, like, oh, that's red, you know, even though maybe to you this would look green, you know, but to me it looks this color, we'd both be like, that's what red looks like. There's a bit of that problem here with the Martian colors guy. And that's why he calls them Martian colors, but he is experiencing something that's different from his phenomenal visual experience.
Does he like,
I'm not sure. I think he sees some colors because there's different kinds of color blindness where you see some colors but not others, right? Oh, my internet connections. Oh, no, it's working.
so
Okay,
like
good.
colors that he still sees in numbers, what colors are you going to see in that circuit?
Well, again, like I'm not really sure. Sometimes it's explained like the numbers literally look different colors. I think it depends on the case,
Yeah.
right? I think for a lot of number color synesthetes, the digits actually look colored, and we know this from different experiments that we can do, like experiments to find out how visually salient certain digits are. But in some cases, it seems different. There's one synesthete named Daniel Tammet who has a very, very, very complicated kind of synesthesia where he experiences numbers as colors, shapes, moods. Every number from 1 to 10,000 has an individual sort of look about it. Yeah.
I don't know if it's the same thing, but I noticed that like my own sort of like mental imagery stuff. If I'm doing like estimates of time on the span of months, the year is always mapped out in a circle, like a clock with years at like the top. And like that's how I determine the distances around like the year. And I cannot. I find
Okay.
that like my brain finds like calendars to be kind of perplexing. Like the sort of like grid, like week system with days works, but I can't mentally translate that to how I think of months.
Yeah. And fair enough. Have you ever seen those calendar calculators? Humans that can count like what, you know, you'd say your birthday and they're like, oh, it was a Wednesday, you know? Yeah, like savants. Daniel Tammet, who I was talking about, can do this.
Yeah.
Anyway, the reason I mention his synesthesia is because, you know, for him, and he writes this out, he's got an autobiography and he's got a book about the mind. They're both really good because he's got like such a weird brain, like that he can like explain like, you know, what it's like you know, his thinking is so different, but he can tell us what it's like. So it's really cool. But anyway, he has a very, very interesting synesthesia where, you know, he talks about numbers being like the number 9 is like the biggest number, not biggest in terms of quantity, but the number 9, he's like, it feels like, you know, it's just huge and imposing.
That's my favorite number because it's so cool. It's like it's 3 of itself.
Yeah.
Like it's also very divisible and
Yeah.
mine is a beautiful
I saw a tweet.
7 because it's the opposite of those things.
Yeah. I saw a tweet the other day. It said 9 should be an honorary even number
Yeah.
because of that. Yeah. And I was like, it like made me chuckle, but yeah. So, you know, Tamit's filming this documentary and he's in New York. And it's like, what's it like in New York? Because he's from the UK in a small town. And he's like, oh, wow, it's like the number 9. I'm surrounded by the number 9, like in Manhattan with all these skyscrapers around him, right? So like the difference between, you know, more typical cases when you're looking at digits and you see color, Tamit seems to have that, but also this other component, because all of his senses seem tied up in his synesthesia, right? So anyway, I know that was a lot, but it's very interesting. And if you get the chance to read any of his books, or there's a documentary he's in called The Boy with the Incredible Brain, I highly recommend you check it out. Tamit is what we call a savant, like Ben mentioned a moment ago. He seems to have got this synesthesia as a result of epileptic seizures he had as a child.
Oh, is he who was on that like talk show?
He may have been. I know he was on Letterman like way back in the day. Yeah, but he so he had these epileptic seizures, but he's also on the autism spectrum. So he's got like just really intense interests, and something happened where, you know, it just all these factors kind of came together, and he can calculate big sums in his head. He can, you know, do calendar calculation. I think at the time the documentary or the documentary was released, he spoke 9 languages, you know. Yeah.
One thing I thought of when you mentioned the calendars thing is the only reason why I know that I was born on a Thursday is because I learned that in like 6th grade, and it explains so many things about it.
Wonder if there's any weird, why are the people partying on Thursdays? What's the connection? You know, some kind of conspiracy here. So how are we doing for time? We've still got a few minutes left. Let's get back to binocular rivalry. How do we explain, you know, this flipping? Like if I show you a boat and a plane, your perception kind of seems to be like boat, plane, like, but not a combination of the two. Well, an early suggestion for the flipping of the percepts might be due to things like eye movements or different things going on in the periphery of your field of vision. But these explanations don't really work. We actually now think that the flip occurs higher up in the information processing hierarchy. We call this like upstream of, you know, of the lower level stuff. But what does this do for us? Why is this important? How does it help us understand subjective conscious experience? Well, in this kind of phenomenon, you have one image becoming conscious, or I would say more conscious than the other image, and then vice versa, and repeat. This is an interesting opportunity for us because it allows us to investigate this relationship here between, excuse me, between objective facts, right, and subjective facts, if you think there are such a thing. We'll just say subjective experiences. Remember, the objective stuff is what's mind independent, right? The information entering the eye from the external world travels up to the early visual system all the way to V1. We'll call that objective. The subjective experience side is, you know, like the flipping of an ambiguous figure, or the flipping of, you know, images in binocular rivalry. We looked into this back in the day. these two thinkers, well, three thinkers, Logothetis and his colleagues, they looked into this using macaque monkeys. Macaque monkeys are these little monkeys that you can actually train to do certain things. You can train them, for example, to report an image they're seeing by pulling a certain lever. So if it's this image, pull this lever. If it's that image, pull this lever. No problem. We can train them to do that. And we can actually do binocular rivalry experiments with these monkeys. So we can sit them down and have them, indicate which image is flipping, how it's flipping by pulling these levers. And their experiences seem to be a lot like our own experiences, at least so far as we can tell, because the monkeys can't exactly, tell us what's happening, right? So when we'll do an experiment like this, we show them, say, a vertical grading in one eye and a horizontal grading in another eye. So just lines, right? Which way are the lines going? Are they horizontal or vertical? And if we show the different gradings to different eyes, or if we show gradings moving in different directions, the monkeys actually indicate via their lever pulls that what they're seeing is flipping. So monkeys, and one assumes great apes as well, are actually susceptible to the same kinds of ambiguous figures and binocular rivalry that we are. And that's because their brains are similar to our brains, right? So Logothetis and his colleagues trained these macaques to do this. They recorded the brain activity using single cell recording. So not only did they have the lever pulls, or the lever pulls, they could actually see what's happening in the brain at the same time. So they looked for what areas in the brain there was activity and whether it correlated to the macaque's perceptions, their changing perceptions, not the unchanging inputs shown in front of their eyes, right? Because remember, it's not like we're showing them one thing and then showing them another thing. The same thing is there the entire time, right? Now, cells in the early visual cortex were found to respond to the unchanged visual input, right? And there were certain cells, certain neurons in area V1 that responded just to the vertical stripes, some that just responded to motion, some just to horizontal stripes. But the cell's activity didn't change. So the processing in V1 looked the same throughout, even though the monkeys were reporting a difference in their experience, which suggests, like what we learned earlier, that area V1 is not necessary for consciousness. We don't need it. Like when we dream and we have visual dreams, area V1 is not active. This is the job of area V1, to process, the objective visual information from the world. So further up the pathway, like in the motor cortex or in area V4, some cells' activity changed, which seems to have corresponded with the monkey's changing experiences. So when one of the monkeys pulls a lever, there's also a change in those areas of the brain. Also in the inferior temporal cortex, almost all the cells changed their response according to what the monkey reported seeing. And remember, in the temporal cortex, we're dealing with integration of sensory information, right? In this case, visual. So, conscious visual experience needs a lot more than just the visual cortex. It needs the temporal lobes as well. So it seems that the activity in that area corresponded to what the monkey was reporting that it saw consciously, right? So let's see, about 10 more minutes. Do the neural correlates of consciousness or neural correlates of visual experience lie in IT, in the inferior temporal cortex? Maybe. But if we answer yes, there's a problem. It turns on the assumption, a yes answer that is, turns on the assumption that macaque perceptions are conscious in the same way that ours are conscious. I think they probably are, but we just don't know for certain, right? I think it's a safe assumption though. But others don't, right? Some believe that you need language for consciousness. interestingly enough.
So like, what is language though? Like, what's speech and talk and roll?
Yeah, they have communication, but they don't have language. Like language has rules, right? Like language has a grammar, language has like
That's a weird thing. So like, don't I think like our early ancestors were conscious?
what?
That's like saying like our early ancestors were conscious because we have grammar.
Well, I don't know. I mean, I think we were speaking language. Like how long ago are we talking about?
Before the Greek civilization era that we talked about.
I think we're totally still using language.
Oh, yeah.
Yeah,
No,
absolutely.
It's like, I mean, obviously you have sort of like complexity, like communication capacity, like that. It's really, if you're, even by like Bronze Age, if you're going before that, historically speaking, you are well into the realm of conjecture.
Yeah, I mean, like when I think of like modern day hunter-gatherer societies, you know, that are still like living a traditional lifestyle, you know, they're not at a Bronze Age level of technology, right? They don't refine any kind of metals. They're still using stone tools in some cases. But they have language and very complicated language, right? Sometimes not super complicated, like some indigenous communities don't have numbers higher than 3, right?
Another one is colors. They have to know how, like, as
Yeah.
many individual like concept words for colors.
Exactly, like blue and green will be treated as the same color, for example, right?
But we also do have some colors.
We do, but you know, the point is, even back then, simpler language is still pretty complicated,
I
right?
mean, there are languages that have like 4 individual words for various colors.
Yeah, yeah. It depends on the environment. Like the Inuit have lots of different words for different kinds of snow, right? People say like, oh, it's so many words for snow. Well, really, it's one word for different kinds of snow.
As someone who is an owner of an Algonquin dictionary, there is an entire page devoted to different kinds of canoes.
Because that matters when, you know, you're living your life depends on being able to navigate a river system and not die, right?
Like, yeah, it's like, where is it? What's it made out of? How many people is it for? What's it used for? What condition is it in? What's it doing? Like,
Yeah. And some from the chat here, transitoriness and displacement, which animals don't have. Yeah. I think animals have a form of communication. All animals have a form of communication, but language is a little different because language has syntax, semantics, rules. So maybe we need language for consciousness, and the people who think this would argue that the monkey's responses, the lever pulls, the activity in the brain, doesn't mean squat when it comes to the neural correlates of consciousness.
I was kind of stupid, to be honest.
Yeah, I think that's silly because why on earth would consciousness evolve? I mean, come on, this is an expensive brain that we humans have, right? We need so many calories to keep this thing running. We need all this oxygen to keep it going all the time. You know, why? Other animals have brains that are, you know, nearly as complicated or maybe even more complicated than ours. You know, the great apes all have pretty complicated brains. Their neocortex isn't as advanced as ours, but still. Whales and dolphins have more folds in their neocortex than humans do.
Those adults are scary, so you think to get up to.
Oh yeah, like they play with their food.
well, even like species of corvids and some of their social behaviors.
Yeah. Yeah, so corvids and other birds like parrots, you know, have a different kind of brain architecture, but they're still incredibly intelligent, some of them.
I mean, you with like, I don't know if it's certain species of either crows or ravens, but I know like they don't necessarily have, you know, language per se, but we can still observe them have, they have social behaviors that are like, you know, if one gets like hit by a car and killed, then they remember, yeah, they'll remember, but they'll also, you know, have they'll have like a social sort of thing they do that is somewhere between a murder investigation and a funeral.
Yeah,
So
yeah,
it's like-
it's true. Like they have a vigil.
Yeah.
Monkeys do that too, elephants. It's crazy. And octopus are pretty smart too, you know, they can pass the mirror test and they don't even have a spine. So,
That's politicians.
yeah. Well, even, I mean, do humans really understand death though?
No,
Right?
I don't think so.
Yeah.
But
So-
I think most people have some sort of theory about death.
Yeah.
Sort of reconcile it with themselves, you know?
Yeah, exactly. What's that? But then if we're dead and if physicalism is true and I'm just my brain, and then when I'm dead, then I'm not really experiencing death
Yeah.
because I'm dead, right? I don't experience, right? So it's like, you know, try not to rack your brains too hard. So anyway, let's move on. Oh, here we're getting into the human side of things again. Maybe we'll leave it here. We can't do single unit recording in most cases with humans because it's too invasive. And this is also why I couldn't be a neuroscientist. You know, if you've got to do brain surgery on monkeys, you know what they do with the monkeys when the experiment's over, right? Like, yeah, they're euthanized, you know? So, yeah, like I don't want to, no. But if you're a cognitive scientist, you don't have to perform brain surgery on monkeys. So it's good. Or you can also work with human participants. fMRI is getting a lot better. So maybe we can use fMRI to see what's going on in the human brain when there are cases of flips during binocular rivalry, right? So they had their participants wear these stereoscopic glasses, and one had a red drifting grating in one eye, and in the other eye, a green face. And they just had to push a key to indicate which image they were seeing, like which it was flipped to, right? So grating versus face are presented, and they're different enough that the experimenters could investigate very specialized brain areas and the activity therein. You know, areas that are dedicated to color processing, form, but also face perception. Face perception is important because we have a whole area of the brain dedicated to that. It's called the fusiform gyrus. And there's an area on the fusiform gyrus called the fusiform face area. And it is active when we look at faces. Even this, if I do this, if I just put a schematic of a face, even that will get activity going in your fusiform gyrus. So it's pretty crazy. So they searched for these areas where there was higher activity when the face was seen versus when the grating was seen. And when the participants saw the face, the experimenters detected bilateral activity in these occipital temporal areas of the ventral visual pathway, including parts of the fusiform gyrus. That means that right where the occipital lobe and temporal lobes are kind of connected together, we have areas of processing on the ventral visual pathway. Remember, ventral is the one that goes under. So dorsal just means on top and ventral means underneath. So this is basically science for in the part of the brain with the occipital and temporal areas where your ventral visual stream, where your conscious visual stream goes, including the parts of that stream that are implicated in processing faces. So they were able to like see very specifically like, oh, this when the face is, when you're conscious of the face, your fusiform gyrus is lighting up, your ventral visual pathway is lighting up. But if you're watching the grating, maybe it's like lower level stuff that's lighting up. And I'm saying lighting up loosely. Don't use that in an essay if you talk about neuroimaging. Yeah, because lighting up, it's not, nothing's lighting up. What we're seeing when we see an fMRI, we're seeing what are called voxels. A voxel is like a three-dimensional pixel. That's what it means, volumetric pixel. So it's like a little cube, and the color indicates the level of activity based on the bold signal, which is the blood oxygen level dependent signal. Yeah, because oxygenated and deoxygenated hemoglobin disrupt magnetic fields differently. So we can use that difference to see where the most blood is flowing to, and that gives us a stronger bold signal. I don't know. Even when you're asleep, though, your brain is going like crazy, right? You know, it's like that 10% of your brain myth. You know, it's just wrong. You know, but like in all seriousness, how can anyone believe that? Yeah. I got into a conversation with a guy about that once. Like, you know, you only use 10%. And I was like, hang on. I teach philosophy. I'm a cognitive scientist, and that's wrong. He's like, but I heard. No, think about it. If you only use 10% of your brain, like, what's the rest of it for? Why? Are we like the ancient Egyptians now? The brain doesn't do anything, or the brain is cushioning for your eyes or your skull? Like what?
I mean, I'm upset because I was under the impression that that was true. If I used more than 10% of my brain, I might be a function.
Well, maybe you're not using all of your mind. But we use all of our brain, right? But do we use all of our mind? There's definitely, like, most of what's going on in the mind, we are absolutely unconscious of, right? And I think maybe that's where that myth comes from. Equivocation between the brain and the mind, right? So, well, yeah. If you ever, yeah, well, like we know from brain damage, right, that the mind depends upon the brain in some important way, right? And some cognitive scientists even just call it the mind brain, like one unit together. And if you want to sound neat and interesting, you can say that too. Like, I study the mind brain in my philosophy class. Sounds pretty neat, right? So that's it. Okay, thanks. Zoe says she's only ever 30% conscious. That's how it feels like over the pandemic. I'll tell you. Yeah, I sympathize. But thanks everybody who joined online. Thanks everybody who came in person. I'm going to leave this right here. Yeah, maybe it'll make someone's day.
Tell them that it's a very complex philosophical problem.
It's true. Like, I mean, it's crazy. This is called pareidolia.
Is that the phenomenon where we see faces?
Where you see faces or where you see other patterns that are not. Yeah, because it's safer to assume that Russell in the bushes is a predator. Yeah, it's animism again. Animism. Yeah. Yeah. What?
Very fitting.
Yeah, I should read that. That sounds interesting. Turn off the projector. Screen goes up. See what I was not conscious of what I was doing there? Anyway, okay. Bye, everyone. Have a good day. Yeah. True.